So, in the previous session, we have seen an introduction to multi-carrier modulation. Okay, in today's class, we will be seeing some of the techniques to mitigate subcarrier fading. In the last class, we have seen how to find out the total bandwidth for non-overlapping channels. Am I right? The last class, we have done a problem also. We have found out how to find the total bandwidth of a non-overlapping channels. Non-overlapping channels means you have a bandwidth. It is equally divided into n small subchannels, and these n subchannels are not overlapping. That means one will not cross over to the other. Today, what we are going to see is what happens when two subcarriers or substreams or subchannels are overlapping with each other. The spectral efficiency of multi-carrier modulation by overlapping subchannels. This is what is the next topic in our syllabus. The subcarriers form a set of orthogonal basis functions on the interval 0 to Tn for any set of subcarrier phase offsets phi I. Let us take subcarrier phase offsets to be phi I. Okay, all these are orthogonal channels. And we have a total interval from 0 to Tn, where we have n number of subchannels. Zero to Tn is the interval, and we have a set of orthogonal basis functions for each of these carriers. Now, in case of overlapping channels, the total bandwidth is defined as B is equal to n plus beta plus epsilon by Tn. In non-overlapping channels, how it was defined? It was defined as B is equal to n into 1 plus beta plus epsilon by Tn. This was how we defined the total required bandwidth for overlapping channels. Sorry, for non-overlapping channels. For overlapping channels, the equation, the total bandwidth is given by B is equal to n plus beta plus epsilon by Tn. Now let us compare the bandwidth of a multi-carrier subsystem with overlapping subchannels and non-overlapping subchannels using the same parameters for what we have done in the previous session. We have done an example. Now we are going to compare the difference between overlapping subchannels and non-overlapping subchannels. Consider an OFDM system. So in detail, what is OFDM system we'll be seeing in the coming slides. But now let us consider an OFDM system operating in a channel with coherence bandwidth BC. BC here is given as 10 kilohertz. Coherence bandwidth is 10 kilohertz. Now the question is, find a subchannel symbol time Tn, which is equal to 1 by Bn, which is equal to 10 times Tm. assuming that Tm is 1 by Bc, so that we get a flat fading channel. The condition for a flat fading channel is that the coherence bandwidth should be greater than the input signal bandwidth. Now the second question is that let us consider we have n subchannels with 128, with n is equal to 128. If we have a raised cosine pulse with beta 1.5, if the additional required bandwidth for minimal power, that is epsilon, is 0.1, then you are asked to find out the total bandwidth of the system. The third part of the question is that find the total bandwidth required for the system using overlapping subcarriers separated by 1 by Tn, and compare your answers with the overlapping subchannels. So we have two conditions here. In the first one, we have overlapping subchannels. Second thing is non-overlapping subchannels. We are going to compare these two things. Let us now solve this problem. So we know that for non-overlapping channels, the total bandwidth B is equal to n into 1 plus beta plus epsilon by Tn. So we are considering here first non-overlapping conditions which we have seen. We have seen one problem in the previous class also. Now we are finding out the total bandwidth B, which is equal to n into 1 plus beta plus epsilon by Tn. So we have been given all these values. N is 128, beta is 1.5, and you get epsilon to be 0.1, and you have been given the value of Tn. If you substitute these values, you will get 332,800 hertz. So this is what we get for non-overlapping subchannels. That means the total bandwidth, whatever we have B, is divided into n subchannels where there is no overlapping between two channels. Now let us consider the second case where we have channels being overlapped. The total bandwidth for overlapping subchannels B is given by B is equal to n plus beta plus epsilon by Tn. Substituting all the values, n is equal to 128, beta is equal to 1.5, and epsilon is 0.1. I'll write it here for easy understanding. N is equal to 128. We have 128 subchannels. Beta is given to be 1.5 and epsilon is given to be 0.1 into 10 raised to minus 3 seconds. Sorry, that is T. Epsilon is given to be 0.1. Value of epsilon is given to be 0.1, and Tn is given as 0.1 into 10 raised to minus 3 seconds. Substitute these values for overlapping subchannels. So we get the total. So on finding out both these conditions, what we come to understand is that the total bandwidth while using overlapping carriers is less than half of the non-overlapping bandwidth. So the total required bandwidth is for overlapping carriers is half of the non-overlapping carriers. Now let me ask you a question. Suppose you are asked in your university exam a question to prove that the total bandwidth required for a non-overlapping channel is half of the, or is double the overlapping channels. How you will prove it? I believe all of you have really understood what we have been discussing so far. Am I right? I've given you an example also. Now I am asking you a logical question that you have to prove it. Suppose a proof is asked, will you be able to do it? Yes or no? Very easy, right? Next important topic that we are going to discuss is about mitigation of subcarrier fading. The advantage of multicarrier modulation is that each subchannel is relatively narrow band which mitigates the effect of delay spread. Each subchannel experiences flat fading which can cause large bit error rates on some subchannels. If the transmit power on subcarrier I is Pi, and if the fading on that subcarrier is denoted by alpha I, then the received signal to noise power ratio gamma I is given as alpha I square Pi by N naught Bn, where Bn is the bandwidth of the subchannel. So we are always presuming that we are dividing these subchannels, this whole bandwidth into equal number of subchannels, so that the bandwidth of each subchannel will be B by N, where N is the total number of subchannels and B is the total bandwidth. So for each subchannel, let us consider the bandwidth of each subchannel to be B suffix N, Bn. Okay, B is the total bandwidth. We are dividing this total bandwidth into N number of subchannels. So we are calculating the signal to noise ratio, where Pi is the power of the ith subcarrier and fading is denoted by alpha I. We'll get gamma, that is SNR on the ith subcarrier, that is gamma I is equal to alpha I square Pi by N naught Bn. N naught is the N naught by 2 is the power spectral density of the ith input signal. This is a very important question. Because of flat fading, because flat fading can seriously degrade performance in each subchannel, we are making all the subchannels to be a flat fading channel where we are reducing the input signal in such a way that it is much less than the coherence bandwidth, so that all these signals experience flat fading conditions. In frequency selective fading, what happens is that the coherence bandwidth is less than the input bandwidth. Okay, here we are assuming a flat fading condition so that there can be a very serious reduction in power. That means there is a degrading performance in each of the subchannel, and it is important to compensate for flat fading in these subchannels. So you may be facing a question like, what are the measures to compensate for the flat fading in multi-carrier modulation systems? So the answer for that question would be, the commonly used techniques for compensation for flat fading in subchannels are: the first one, coding with interleaving over time and frequency, frequency equalization, pre-coding, adaptive loading. This is a very probable question, one of the teacher's favorite questions to be asked in your exams. What are the measures we take to compensate for the degradation caused due to flat fading in multi-carrier modulation systems? The four important techniques are coding with interleaving over time and frequency, frequency equalization, pre-coding, adaptive loading. So we'll see that in detail. The first one, coding with interleaving over time and frequency. What is that? How we are going to mitigate, or we are going to reduce this flat fading by coding with interleaving over time and frequency. The basic idea in coding with interleaving over time and frequency is to encode data bits into code words, interleave the resulting coded bits over both time and frequency, and then transmit the coded bits over different subchannels such that the coded bits within a given code word all experience independent fading. Unlike other fading mitigation techniques, coding with frequency or time interleaving takes advantage of the fact that the data on all subcarriers are associated with the same user and can therefore be jointly processed. So here we are going to encode the data, that is coding with interleaving over time and frequency. The title gives you a good hint about how we are going to proceed with. We are going to encode the particular data bits into code words and then interleave the resultant code word with the time and frequency and then transmit over the different subchannels. The advantage of the first method, that is coding with interleaving over time and frequency, is that it takes the fact that the data on all subcarriers are associated with the same user and can therefore be jointly processed. The second one, frequency equalization. The first thing we have seen, that is coding with interleaving time and frequency. The second one is frequency equalization. In frequency equalization, the flat fading alpha I on the ith sub-channel is basically inverted in the receiver. Specifically, the receiver signal is multiplied by 1 by alpha I, which gives a resultant signal power alpha I square pi by alpha I. While this removes the impact of flat fading on the signal, it enhances the noise power. The disadvantage of frequency equalization is that the noise power increases. When you are asked to discuss, when the question is discuss the various flat fading mitigation techniques, you need to discuss the disadvantages also. When you discuss the disadvantages and advantages of each of these techniques, you get more marks. So the disadvantage here is that the noise power is increasing, or it gives more, emphasis to the noise. The second technique that is used for mitigation is frequency equalization. Okay,